We welcome you all. And today in our Mom Talks, we have Professor Wagner from Weizmann Institute of Science. We'll be talking about extremely skill-dependent mechanical properties of epoxy fiber. Professor Wagner is a well-known name in the area of composite materials and interfaces. So, working in that area, I'm sure you must have heard of him. He did his PhD from Hebrew University in 1983, and then he joined Cornell University as a postdoc, and then he joined Weizmann later on. He has written about 300 scientific papers and chapters, and his research interests include macromechanics of advanced composite and their interfaces, carbon nanotube and nanocomposites, mechanics of natural and nature-inspired structure. He has received many awards, including uh, Israel Vacuum Society Research Award, Medal of Excellence in Composite Material, Landau Prize, and Plantin Award. He was also guest professor at École Centrale Paris and Exxon Mobil Research and Engineering, New Jersey, and Max Planck Institute. So, and there's a long list. So I'll just not take too much of time, and then I'll hand over the stage to Professor Wagner, and let's listen to him. Okay, Professor Wagner, it's yours.
Thank you. Thank you very much. I would like to acknowledge the opportunity to give a lecture here. So thank you, Professor Agni-Rotri, Professor Basso. It's a pleasure to give a lecture to people from all over the globe, actually. And let me tell you something about the Weizmann Institute first, because you may not know where we are. So this is a map of Israel. It is a very small country, actually, Israel. And we are in Rehovot, which is located somewhere between south of Tel Aviv and west of Jerusalem. This is 25 kilometers south of Tel Aviv, 45 kilometers west of Jerusalem. The population of Rehovot is 120,000. The size of Israel is not very long. From Eilat at the extreme south to Nahariya at the north is about a little less than 500 kilometers. And from the sea, where the Gaza Strip is, and the Dead Sea, so that's the Mediterranean Sea, there is about 100 kilometers. So we are very small. Sorry. So this is another view of the same map. We are on the blue dot there, and that's the length and the width, which I just mentioned. And if you compare that to India, it's about the distance between Kolkata and Kathmandu in Nepal. So this gives you an idea of the scale of our country. We have, at the Weizmann, we have 5 faculties: math and physics, chemistry, and 2 faculty of biology, actually biochemistry and biology. And we have a science education institute as well. We are a small institute, 2,700. We are much smaller than the big universities in Israel. We are a research institute, and we don't have undergrads. We have 250 professors, 600 engineers and technical staff, 1,200 students, among them close to 180 Indian students, actually. We have a big Indian population and also a big Chinese population. And as I said, we have only master and PhD. We don't have undergrads. 220 postdocs and 400 administrative employees. So that comes up to a total of about slightly less than 3,000 people. We are the only academic institution in Israel where everything is done in English. And the reason is, well, there are a few reasons, but we have many students and postdocs from abroad. And also English is the international language of science. So it's very convenient. The institute was founded in the 1930s, 1934. There were very few buildings, and we have grown quite extensively these days. The motto of the Weizmann is really that we are trying to do science for the sake of science, and the primary drive is curiosity. We're trying to stick to that, and so in principle you can do whatever if you can get the grant and have the money for doing something. You can basically do whatever you like provided, of course, that it's of a very high level as much as possible. Now, there is another interesting thing at the Weizmann is that about half of the institute is biology, actually, so the people in the life sciences. And so most of us, mathematicians, chemists, physicists, etc., are involved in projects that are related to biology. That makes things very interesting, and the interdisciplinarity is extensive at the Weizmann. All right, so let's start the lecture, and I would like to talk about the extreme scale dependent mechanical properties of epoxy fibers. Epoxy fibers, which I've indicated in red here, because fibers of epoxy are not easy to make, and they are not made usually. And so why on earth would I do something like this? Well, so the question is, why slender epoxy specimens, really? There is relevance of slender specimens like that, epoxy specimens, relevance for thin films like optical films, adhesives, sealants, coatings. And so it's interesting to have specimens to be tested. There is also relevance for fiber composite materials. I'll show you that in a second. The reason we are interested in slender specimens in general is that the mechanical behavior depends very much on the size of the specimens. Film thickness and fiber diameter are key parameters when measuring mechanical property. And also because it's difficult to make. And this is something I wanted to do for many years, to find the right student which is obstinate enough to be able to address this challenge of preparing very thin fibers and films of epoxy. 2 weeks ago, exactly on the 3rd of November, there was a paper that was published on this issue. And there are very, very few papers published on this, maybe 4. One of them being ours, which was published last year in the summer of 2019. And this paper by the Belgian group of the Clerc deals exactly with that, in situ observation of microscale ductility in a quasi-brittle bulk scale epoxy. So let me show you what I'm talking about. The relevance to very thin areas of epoxy or polymers in general in a composite is indicated here. In this case, you have an interlayer between fibers. Those fibers, I think, are glass fibers. So they are of the order of 10 micron. And there is a very thin nanometer scale or size interface. And this interlayer is somewhere between 10 and 200 micron. But if you have a well-compacted composite, then this area, this zone is very thin, and it can go, here it's indicated, this is from that paper that I just mentioned, it's between 1 and 25 micron, but actually it goes much smaller. And at that kind of dimensions, you really have very strong size effects, as I showed. You can easily calculate the layer thickness between fibers, which decreases as volume fraction increases. You can assume an hexagonal packing, and you have this standard geometrical expression here, which gives you the thickness between two fibers, which are very close to each other, as a function of the fiber diameter, the volume fraction, overall volume fraction, and a numerical parameter. And so, as you can see, the interfiber distance, edge to edge, is decreasing as you increase the volume fraction, as we imagine, but we are going actually the other way around. And sorry, we are going this way. and the thickness becomes submicron once you reach a volume fraction of about 65%. So submicron things become very interesting. And there are implications of the thinness of those epoxy layers, as I said, on the mechanical properties. Now, how do you make them? That's a real experimental challenge. And there are extremely few attempts in the literature to make those. Bodo Fiedler made some in 2007, then in Germany, then Gillespie in the States a few years ago, and Bodo again also, Fiedler. And we have published a paper where we have used Epon resin, which is a standard epoxy resin, is GEBA, diglycidylated bisphenol A, and it's hardener, which is a polyethylamine. And the fiber was prepared by hot drawing and curing simultaneously, roughly following this literature here. It's not easy. So how do we do it? We mix the resin with the hardener, we degas, and we heat at 80 degrees in this case to almost reach the vitrified state, and the viscosity is optimized for fiber drawing. That's where you then extract a small amount from this reservoir here using a spatula or a needle, and you hang this at a height of about 1.5 meters in our case, until a thin fiber gradually forms. And this is just because of gravity, and it cools down to ambient room temperature very slowly. So this is what we do here, and then after that, what you do is simply once it's pure, you fix the fiber on a garboard, which makes it ready for testing with a tensile testing machine. The final fiber diameter is determined empirically or semi-empirically by modifying the amount and the viscosity. You're playing around with those parameters at the tip of the spatula. The fibers are cured at room temperature for 48 hours and then post-cure at 80 degrees for 5 hours. So this is a technical thing. It's critical in this case, because if you don't follow very carefully something like this, you are unable to make epoxy fibers. This refers to the paper that we published last year, and I will refer it constantly during this lecture. The fiber looks very good. Once you are able to make it properly, it looks very clean, smooth, high quality. There are no surface defects or apparent surface defects. The material is clear and transparent, and the cross-section is circular, and you can cut it then later into smaller specimen for mechanical testing. And this is what I want to show you now. The range of diameter that we were able to prepare in this first set last year, or 2 years ago, was between 20 and 350 micron, which is smaller than anything else actually that exists in the literature, including those other papers. Let's talk about epoxy now. Bulk epoxy is an archetype of amorphous isotropic polymer, and it's brittle typically. When stressed under the tensile force, it doesn't resist
Professor,
crack.
sorry to interrupt. Can you please adjust your mic because we are losing your voice sometimes. Maybe the mic is too far away from your.
Oh, it's stuck to me, so I don't know. All right. So can you hear me now? Maybe I should.
Yeah, this is much better. Yes.
Oh,
thank you.
Then I'll talk stronger, louder. Under tensile force, there is poor resistance to crack initiation. This is epoxy. This is how it looks like. This is how the break looks like. And the nominal strength typically is around 70 megapascal, while the failure strain, you can play with the failure strain, but it's somewhere between usually 6 and 12%, the strain. And the toughness here is 5.1, but that's less relevant at this point. I want you to remember this value here, and the modulus is 1.1, 1.2 gigapascal usually. But the 70 megapascal here is important, and 12% failure strain is also important to remember. So this is a typical failure of epoxy. Now, if you make a test, if you test the epoxy fibers, things look different. They look like this. Once you increase uh, the stress or the strain on the epoxy fiber, which is here, you generate, where the arrow is, you generate necking. This in itself is amazing. I mean, epoxy doesn't neck like a metal or something like that, or like a thermoplastic material, such as polypropylene, for example. There is no necking usually in epoxy. And so this was a big surprise. The elongation is very large, and necking is unusual for amorphous crossing polymer, as I said, and this is how it looks like under the microscope. You see, the necking starts here, then propagates. We just cut the ends so that you can see this necking picture. Now, no less impressive and surprising is the stress strain curve. Bulk epoxy is in black here. This is the typical stress strain curve of bulk epoxy. As you see, it reaches around 60 megapascal, as I said, 60, 70, and the strain goes up to 15% or 12% or 10%, something like that. But now the fiber we prepared is in red. This is the fiber we prepared. The modulus is higher, as you can see from the slope here. And then there is a yield point and there's a very long plateau. And then there is cold drawing. I mean, the modulus increases again, and the strength increases again, and goes quite high, above 100 megapascal. So it's about double the value for the bulk. Then, if you stop the test here, and you have all this is necking, you stop the test, you cut a piece and you retest this necked fiber here, it goes according to the blue line, which goes now to the sky, really. It goes to 100, 250, 280, and sometimes more megapascal. So this is a huge surprise. And let me show you this in a table. This is the value for bulk, and also for fibers that have a diameter above 120 micron. This is the value for the fibers then increases from 67 to 79 in the diameter range, up down to 80 micron, and then down to 40 micron you reach 112 megapascal strength, and then below 40 micron you have 134 megapascal, which is, I mean, it's amazing. There are other data here, but it's not necessary to talk about this right now. If we test the necked fiber, which were in blue on the previous slide, what you get is even higher. Actually, you go up to a strength of 227 on average for necked fiber below 40 microns. So this is really a very, very large value. You can do the calculation also for true strength by dividing by the evolving cross-section, the true cross-section, and get higher values. But it's not critical to talk about this right now. So let me show you a plot of the strength for the as-prepared fibers, which are here compared to the bulk value, which is this dotted line here. And the nominal value is plotted in full symbols, and the true value, as I mentioned before, is plotted in open symbols. And you see that below a certain diameter, which is around here, 90 micron or so, you get this increase from the 67 megapascal value up to close to 200. And if you calculate the true strength, it goes even much higher. Then you have the strength of the necked fibers, which again is compared to the bulk value, and you get numbers that are really almost unbelievable. The very, very high. And the question is, what's the origin of this size effect on strength? Because in none of the papers that were published before, the 3 or 4 papers that were published earlier, nobody addressed the question of, what's the physics behind this thing? What's going on? Why is there such a huge size effect? And so we wanted to address this. This size effect has been known for a long, long time, from Aristotle, actually, who was asking, why are sticks of wood weaker as they are longer? And then Da Vinci also did some very well-known testing of iron wires of various lengths. And he stated that among cores of equal thickness, the longest is the least strong. Galilei published 2 new sciences, and I warmly recommend to read this book because it's amazing. The discussion between the protagonists there is really fascinating. He demonstrated the reason that a large structure proportioned in exactly the same way as a smaller one must necessarily be weaker. And so he did that with wires with different lengths as well. The most surprising fellow who studied, or scientist who studied this size effect, is Mariotte. Is the well-known Mariotte scientist who did research on gases. The Boyle-Mariotte study is well known, and he states that a long rope and a short rope are always support the same weight, unless that in a long rope, and that's the key, there may happen to be some faulty place in which it would break sooner than in a shorter. So he addressed the reason why the size effect occurred. And then came Griffith, of course, which was the first, so-called first, but actually Mariotte did it before, related the presence of flaws and the specimen geometry with strength. He stated that the weakness of isotropic solid is due to the presence of discontinuities of flaws. So he really assumed that there are flaws, there are always flaws in materials. And so he concluded that the effective strength of technical materials could be increased 10 or 20 times at least if the flaws could be eliminated. Of course, this is well known today. And so this is a first address of the size effect. And this is from the original paper of Griffith, 1920. So I took the data and I plotted them. I transformed the units to units I know better, which are micron and Pascal or megapascal. And this is where what I got. And the strength is proportional to the diameter. Looking at diameter, not length, raised to the power minus 1/2. This is what Griffith expression or model leads to. And so we have bulk glass 170 megapascal or less, and the extrapolation goes up to the sky for glass. Then we have Wallaby-Weibull, who introduce a probability distribution and the size effect. And the size effect is, in this case, gives the scaling law that goes as delta to minus 1 over b, and b is a shape parameter, and a is a scale parameter, which actually is nothing else than the mean strength of distribution. So the schemes are empirical. I didn't mention that, but some people also derived the strength as being proportional to 1 over the diameter. It's deterministic. This is the classical vacuum mechanics argument. And then there is stochastic, where B is a function of the material, is generally larger than 2, where 2 is the vacuum mechanics exponent, or 1/2. In all the models, the presence and the size of critical defects plays a role, of course, and we have these scaling laws here, as you can see, but that doesn't give us much novelty here. So now we conclude using our data that the Griffith and the Weibull scheme both appear to describe reasonably well the diameter of the strength of both types of epoxy fibers. You see the slope is 1/2 for the LEFM, and there is quite a lot of spread in there, but especially for the fiber, the necked fiber has a lot of spread, but the slope is still going through in a reasonable way for the fiber. The fiber distribution gives you two plots, on the left for as prepared fibers and on the right for the necked fibers, and the Weibel model fits quite well. It's been sorted in 4 diameter ranges, and the effective diameter on the strength, as expected, appears as a shift of the data. Is there anything else in the literature regarding this? Well, if you dig deep enough, you find things for polymers, I'm talking. You see 1984, there is polyethylene. The strength is plotted as a function of diameter. And for polyoxymethylene, you have also very few data points, but there is also a slope of 1/2 for polyethylene and -1/2. And 0.9 minus 0.9 or for polyoxymethylene, that's not very good in terms of the models. And then we have polyacetylene of various brands, again in the 1980s. So things exist. And we have other properties that we've measured, and they also have a size effect. Young's modulus has a size effect, and it's way above the bulk value of epoxy Young's modulus. As you can see from below, it's 3 times or something like that on average. The strain is also much larger, but we know that because of the yielding. The yielding is totally unusual for epoxy, and this is what we see. So we have that. And so there is a huge difference between bulk epoxy as we know it and those necked fibers, or those thin fibers. Toughness also has a toughness being simply here the area under the stress strain curve, and the toughness is also having a size effect. There's a dependence on diameter of both for as prepared and necked fibers. So we have that. We have all this data, and there is also another set of data which is not ours. And it's not with epoxy. Well, it is ours actually, but it's not with epoxy. And it's electrospun polymethyl methacrylate fibers. And again, we have an effect of the diameter on Young's modulus, on the strength, and on tensile toughness. This is work we did a long time ago, 10 years ago, something like that. And we observed also a size effect for very thin nanometer size electrospun fibers, PMMA, not epoxy. Okay, and then a little bit more polypyrrole nanotubes and electrospun polystyrene fibers also show a size effect in the range of microns and submicrons for the polystyrene fibers, and in the nanometer range for polypyrrole. So this is really a universally observed phenomenon. In the few previously published works on epoxies that I mentioned earlier, they also observed necking in plasticity. But necking in particular, sorry, the authors attempted to avoid these conditions and to minimize plasticity effects so that they would deal only with the brittle failure mode, because they couldn't explain it probably. And so they tried to avoid explanations regarding, they try to avoid talking about this for the size effect. There is another really amazing observation both for our data and the previous data, is that usually materials never reach their theoretical strengths. Maybe carbon nanotubes or diamond reach theoretical values, but for most materials, or single crystals, but for most materials, you never reach the theoretical strength of solids. What is the theoretical strength of solid? There is a rule of thumb, which is take the Young's modulus, divide by 10, and you get the theoretical strength. It's really not witnesses, or rarely witnesses. And here it works. It's observed for epoxy fibers because the modulus is on the order of 3.5 gigapascal. and the strength is 350 megapascal. So you have exactly E divided by 10, which is really impressive. The question I'm asking once again is what's going on? What's physically happening to the structure of epoxy, which is a cross-linked material, when it's tested in a fiber form below a certain diameter? And if we remember, especially that it's homogeneous, isotropic, amorphous, cross-linked material, polymer. So what's going on in epoxy, which is amorphous and cross-linked? And we then did wax, which is wide-angle X-ray spectroscopy. And we got the first evidence that these highly cross-linked necked epoxy fibers do exhibit macromolecular anisotropy, reorientation of the molecules, partial reorientation, and that likely explains the observed mechanical characteristics. This is something that's never been really done for amorphous cross-linked polymers, of course, because in a thermoplastic you can imagine that the molecules are easily reoriented when straining them, straining the specimens. But with epoxy, which is highly cross-linked, and this one is highly cross-linked, you don't expect that. But there is some molecular reorientation. This is the evidence that we found. You see, when you have an arc shape like you have on the left picture, it means that you have an oriented fiber, actually. And we did some calculations using the orientation parameter, the Hermann-Platzek orientation parameters, which you can calculate from the wax data for the next fiber, and it's 0.23, which demonstrates that it's not a very high reorientation, but it's not negligible. Okay, if you had a value of 1, you would have full alignment with the fiber axis. And of course, you cannot have that in epoxy, which is cross-linked. But nevertheless, we get molecular orientation. We are currently busy doing many more tests, both mechanical and spectroscopic with wax and others, other techniques. And we are also using epoxy films and fibers, but the films usually show no preferred orientation, and the as-prepared fibers do not show the preferred orientation. So really, that means what? That means that the size effect that we observe is different for the as-prepared fiber. It exists because there is a size effect, but it's different than the size effect that we observe with the necked fibers, in which you definitely have some reorientation. All right, so this is taken from books on physics of polymers. This is polyethylene, which is not an amorphous polymer, but this is what you see on the left for the isotropic part of polyethylene. And once you get a neck or in the middle of the shoulder between the unoriented part and the neck, you have these arcs that I showed you before for epoxy. And if you have a full reorientation, you get at the right picture, you get very clear picture of reorientation in the neck of a cold drawn polyethylene sample. So we see a little bit of that. Or the picture we have is more the picture that appears at the center of this figure here. And so we have partial reorientation of epoxy molecules or structure. So defects, in fact, cannot explain the extensive plastic deformation that we see in the experiments, or justify size effect in Young's modulus, which is an elastic property. A question we have is, what's the physical structural origin of the characteristic diameter? Is there any way we can predict what is the value of that characteristic diameter? So what's the physics again? Below which the mechanical properties of epoxy fibers start increasing very significantly. Can other techniques provide further evidence of these alignments? We are doing right now polarized micro-Raman, DMA, and SNOM, which are other, SNOM is an optical technique, which we are using to try to find evidence of molecular alignment, and what kind of mechanism can be responsible for this molecular reorientation in an amorphous cross-linked polymer. And what we are doing right now, which is very exciting, I have a student working full-time on this, a PhD student, is doing electrospun epoxy fibers. And so what that will give us, it's difficult to prepare, but we have them. He's been working very hard on this, and what this will give us is the below the submicron range of diameter, and we are down to about half a micron now, so 500 nanometer at this point, using this electrospinning technique that he has developed. So that is very exciting, and we expect to have results very soon. This is the first electrospun fibers of epoxy that we have obtained several months ago, and we are very hopeful that these will show also very strong size effect, diameter effects. If you want to have further info, at least on the micron-sized fibers, this appears in the paper that we wrote last year. Mayank Tiwari was a student coming from India. Also, he was with us for 6 months or 8 months or something like that, and he came from IIT, I think, if I remember right. And this ends my lecture. This is my group at the Weizmann here. This was last year in July 2019. We get support from all kinds of foundations. These are my colleagues and partners. So the picture here at the right is my group last year. And this year we took a picture, and this is how we look like. Obviously, things have changed, and we are not as free as we used to be. So thank you very much for your attention. And if there are any questions, I'll be pleased to try to answer.
Okay, thank you, Professor Wagner. I think we have a couple of questions in Q&A box. So, yeah, so audience, you can type your questions in your in the Q&A box. In the meantime, I'll read out the questions which I got so far. I think it's one from Arun, IIT Kanpur. He's asking, what shall be the difference between fibers and necked fibers in terms of the preparation process?
Okay. So the preparation process, with the preparation process, as I showed on that figure, the experimental figure, we prepare it by, with a spatula, and we then polymerize the fiber. So that's how you prepare a fiber, the way you expect it. You don't prepare really a necked fiber. You do a test, a mechanical test, and at some point the fibers, the as prepared fiber is necking, okay? And you don't run that test to the fracture end. What you do is you stop it at some point, and what you have is a necked fiber. And that's, if you wish, this is the preparation process for a necked fiber, but it's just after testing and stopping the testing before a final fracture. So you have a necked fiber, which you can test again.
Okay, Arun, I think if you have any doubt, just let me know. And I think Professor Basu has a question.
Yeah. My question is this. We have also seen this on polystyrene micropillars. I mean, polystyrene micropillars also have a sensitivity to diameter. Their compressive strength is sensitive to diameter. So I was wondering whether this is a surface effect. So when you make very thin fibers, do you probably have a surface layer which has significantly different properties than the bulk inside? So as the diameter increases, the surface layer becomes a larger and larger portion of the diameter and starts to have something like a surface elastic effect. It's like putting a wrapper around the fiber.
Yes.
do you think that can be the reason?
If I remember right, I heard an explanation of that sort maybe 10 or 12 years ago for a completely different material, where it was explained the way you just mentioned. And I have a colleague at the Technion who examined this explanation and came to the conclusion that this is not the explanation. Actually, it cannot work. He did some calculations and reached a conclusion that it cannot work. So it's probably not the right explanation. I don't remember his explanation exactly. I can't remember, but this was not further considered as a possible explanation.
Uh, One explanation, I mean, the explanation that a thin fiber does not have as many defects as a bulk probably does not hold in this case, because if it did, then it would have scaled with the length of the fiber as well. But your results don't seem to scale with the length of the fiber; it scales with only the diameter. Or
yes, we didn't do any test on the length effect here. Okay, so there is probably also a length effect, but we are interested really in the diameter, specifically in the diameter effect here. You have to be careful when you invoke the presence of defects and so on, because what really counts is the critical defect. Okay, and when you have a very thin fiber, there is a lower probability of finding a critical defect in the specimen, simply because there is no space, and so the fiber is very strong.
Okay, thank you.
There is another question here.
Yeah, we have one more from Guru Prasad. So he's asking, are the fibers circular in cross section along the length? If it is non-uniform, is the actual area taken care to determine the strength?
They are almost perfectly circular in cross section, yes, along the length. It's very uniform, very clean, but you can always take I see, the actual area taken care. Yeah, no, it's uniform. It's uniform along the length, so that's no problem. However, when you do a test, of course, the fiber shrinks because of the necking, and then you have to take that area into account, and then you have the true strength instead of the engineering strength. Okay, but it's very uniform along the length. They are very clean, very nice.
Okay. So I don't see any more questions.
Okay.
So let me thank you and clap for you.
Thank you very much.
And thank you for this talk. It was really interesting to see these experimental results, which are very exciting.
Yeah, amazing. Really, they are really surprising.
So yeah.
Okay.
So hope to have these interesting papers from you again in future as well.
All right. Okay. Thank you very much for inviting me again.
Thank you.
Thank you.
Okay, bye-bye. Bye-bye.
So, sir, shall I close the meeting now? Okay. Okay. Thank you, everyone.